Listen up. Let me just help you get started on this. So what you're doing here is you are working for some fine fast food restaurant. I don't know what it is. What is it? That's Monarch Burger. Okay, right there, Monarch Burger. And your team has been called in to solve a problem encountered by a fast food restaurant. They believe that their coffee should be brewed at 170 degrees. However, at that temperature, it is too hot to drink, and a customer who accidentally spills the coffee on himself might receive third-degree burns. That's bad. Actually, my wife in high school, she worked at McDonald's, and she was working behind the counter, and coffee spilled on her. She got burned. She's okay and everything, but they were like really afraid that they might sue her and stuff like that. So it is a real problem. Okay. What they need is a special container that will heat the water to 170, brew the coffee at that temperature, and then quickly cool the coffee. Cool the coffee to a drinkable temperature, say 140, and hold it there, or at least keep it. Did I start recording? Oh, yeah. And at least keep it between 140 and 120 for the longest period of time, for a reasonable period of time without further cooking. To cool down the coffee, 3 companies have submitted their proposal. So what you're trying to do here is, where's my, oh, I have to get my tools here. So what you want to do here is I'm going to make a little graph that kind of looks like this and looks like this, just to kind of sketch what this thing is going to look like. You're going to have your coffee is going to start at some temperature, which is not, this is not the 170 degrees. So here's your temp. And here's your time in hours, I believe. And your graph is going to look something like this. It is going to approach an asymptote down here. I'll let you figure out what that asymptote is. But also, what's going to happen with this coffee, right? What's going to happen with the coffee is that you want to figure out the best one is going to be, so say this line here is 170 degrees, okay? And this line here is 140 degrees. And this line here is 120 degrees. So you're going to have 3 different graphs that look like this. And I want you to put all 3 on the same graph. You can put on your calculator and then print it out, or you can graph them by hand and sketch them, but I want everything labeled. But your coffee is going to start at some temperature. We'll talk about that in a minute, like down here with letter A. And it's going to get to 170. Once it's at 170, that's the brewing temperature, and you want the coffee that cools down from 170 to 140 relatively quickly. And the reason you want that is because you can't really serve your coffee until it's at 140 degrees, otherwise people will burn themselves. But you also want a coffee, or the container, that will stay from this time to this time, that will stay in this zone for a relatively long period of time. I figured out that when I go to Starbucks, and the coffee cups that they have, for some reason their coffee seems to stay warm in those cups for a pretty long time. And they must have figured out a pretty good container that works. Whereas other coffee companies, like, that time is shorter. You know what I mean? Okay? So what you're looking for, a coffee company where it cools down pretty quickly and then it stays between 140 and 120 for a relatively long period of time. Now the way you do that is you have to use an initial condition. So down here, they give you, let's get back to the regular worksheet. They give you this thing, Newton's law of cooling, right here. And so I'm going to take this section and blow it up. And I'm going to set up the first the first case for you, and then you guys could do the rest. So with this one, it says that the center keeper company has a container that will reduce the temperature of a liquid from 200 to 100 in 90 minutes by maintaining a constant temperature of 70 degrees. Okay, so this is what goes in for what? Because it's kind of hard to tell what all these different variables mean. Okay, so in this case, this is like your initial condition. Okay? The temperature is going to go from 200, that's u sub 0. Okay? That's your initial temperature. Even though you're not actually, this is just when they're testing the containers, okay? It goes from 200 down to 100, right? Down to 100. No, that's wrong. Sorry, I need an eraser. It goes from 200 for the first one. We're looking at this first one, okay? So it goes from 200 to 110. So those.
That's the second.
Oh, I'm looking at the wrong one. 200 to 100 in 90 minutes. So this is your 100, okay? But I wrote 70. So that should be 100 right here, okay? This T, this is your room temperature. So, or the temperature, the surrounding medium they call it, okay? So in this case, for this initial condition, that room temperature, that surrounding medium temperature is 70. Okay? This is the time right there. Okay? So, so that time in this case is 90 minutes. All right? So when you solve, so the first thing you're going to do is solve this for K, and you're going to end up with something that looks like 100 equals T, which in this case is 70, right? Plus 200 minus 70, which is what? Hello? 130. Oh, this is advanced class, so you know that. E to the K times 90, all right? And I'm just not going to do it. You solve this for K. And this will give you your constant for that particular container, okay? Now the variables, these things stay constant. This and this do not change in your equation. So these are constants, 70 and 130. Those are constants, they don't change. The variables in this equation are this and this. So this is where, you know, after you have to figure out how many minutes it will be until your container goes to first from to 170 from that 200. And then you have to figure out the difference in time, right, between when it goes from, so if this is 170 and this is 140, you have to figure out the difference in the time from 170 to 140. So you would plug in, this is a variable, right? And this is a variable. So you're going to be plugging in temperatures in here and figuring out the times over here after you found your constant. Okay? So for letter A, I want you to do all of that by hand. Well, not so much by hand, but algebraically, like taking logs of both sides and all that kind of stuff. Okay? But with question B and C, you could do it graphically. So you could just find the points of intersection on your graphs and stuff like that. But for A, I want you to subtract this from there, take the log of both sides and all that. And then when you get done with all of that, what I want you to do is use it. So first you're going to find the constant for each container, graph each thing using a graphing utility. How long does it take? I would like you to find the constants, at least for number one, algebraically. Sure. Use a graphing utility to graph each relation, labeling your graphs. You can put them all on one graph if you want. How long does it take each container to go from here to here? So you would have to list that. How long will the coffee temperature remain between 120 and 140 for each one? So this is an important thing. This is an important thing for each company. You're going to figure out that. And then you're gonna write a paragraph on the basis of this information. Which company should get the contract with 9newtons? What are your reasons? So you need to kind of write them like a letter. Dear, or we selected the Senate Keeper Company, or what? One as a group. Okay. So are there any questions on what you need to do? If you want to do the graphs, I'll let you graphing calculator and then have me print it out. Okay. I can do that for you, but you got to make sure you label everything and all that kind of stuff. All right? Okay. The end. Yay.